Hi, in this video we are going to talk about implementation of Dijkstra's algorithm. We are going to keep our implementation super simple. We are going to assume that vertex numbers are from 0 to v minus 1 when we have v vertices. We are also going to assume adjacency matrix representation, and we are going to implement a very naive implementation. Then by the end of this video we will talk about optimizations and data structures that we can use. So let's understand the problem statement. We have adjacency matrix representation of a graph and we need to produce a distance array. So this adjacency matrix representation has 4 by 4 matrix, which means we have vertices from 0 to 3. Also, it's adjacency matrix representation of an undirected graph, which means if there is an edge from u to v, that also means there is an edge from v to u. So let's see this example. From 0 to 1 we have 5, from 0 to 2 we have 10, from 1 to 2 we have 3, right? So from 1 to 2 we have 3. So all the edges are represented in a matrix and it's an undirected graph. So you can notice that this matrix, this is identical to this identical to this identical to this. Our output is distance from the given source given is 0. So from 0 to 0 the distance is 0. From 0 to 1 we have 5. From 0 to 2 we have 5 plus 3, 8. From 0 to 3 we have 5 plus 3 plus 2, 10, right? These are the shortest distances. Let's see this graph. We have 3 cross 3 matrix, which means we have 3 vertices, 0, 1, 2, right? These are the weights of these edges, and we have source as 1 this time. So our distance from 1 to 0 is 4. Our distance from 1 to 1 is 0. Our distance from 1 to 2 is 1. So we are given this input. We are also given a source vertex. We need to write a function that produces this distance array. Now please pause this video and try to write down a function that produces the distance array for given inputs. Here is C++ implementation. We have a function Dijkstra that takes adjacency matrix representation of graph, and we have represented the graph using an array of vectors. This is done this way for ease of parameter passing, and an array of vectors can be treated same as a matrix. You can use 2 square brackets to get the values at different indexes. The next parameter that we have is number of vertices, and we have the third parameter as source vertex, from which we want to find out the shortest distances. If you take a look at this implementation, the first thing that we are doing in this implementation is we are creating a distance array, right? And we are initializing this distance array as infinite. The size of this distance array is v. So we are going to use vertices as indexes in this array. We have used a super simple implementation where we are using vertex numbers from 0 to v minus 1 so that we can use vertices as indexes. And we have initialized the distance of source vertex as 0. So this is where we initialize the distance array, and at the end we are returning the distance array or distance vector, right? So this function returns a distance vector. Now what are we doing in the middle? See, the first thing that we do in the middle is we create one more Boolean array, which is finalized array, and this array is initialized as false. So let's understand this with this graph. We have 4 vertices, we have 2 arrays of size 4 each, and we have 0 for source vertex is 0. So we have 0 for source, and for everybody else it's infinite, right? This is done by these lines. And we have finalized array as false. Now what does finalized array represent? This finalized array represents for which vertices we have finalized these shortest distances from the source. Initially no distances are finalized, so we have all as false. And after doing this we run this loop, and this loop runs v minus 1 times. And in every iteration what we do is we pick the minimum distance vertex, the vertex which has minimum distance value, and this vertex is not finalized. So we initialize such a vertex as minus 1. Then we go through all the vertices and we check if these vertices are finalized or not, because we need to consider only non-finalized vertices. And we check if we have already some value for u. If u is minus 1, that means we don't have any value. So in that case we set u, or if we have some value, then this distance I is smaller, then also we update the u. So we update in both of these cases. We have logical OR here and we have logical AND here, right? It should not be finalized, and one of those two conditions should be true. So this is how we pick the minimum distance non-finalized vertex. And this is iteration we are going to pick 0. And after picking 0, we are going to mark it as finalized, right? We mark the 0 as finalized true. And after finalizing a vertex, we are going to go through all the non-finalized adjacent and we are going to relax them one by one. Let us see what is relax operation. say if our current picked vertex is u, u is the vertex we picked in this step, and v is an adjacent of this vertex which is not finalized. So we have certain value of this adjacent. Initially these values are infinite. So what we do here is we check if the current value of distance v is greater than the value that we are getting through u. So if you're getting a shorter path through u, you update the path from source to v using u, right? That's what we call relax operation. So if this distance plus this distance is smaller than this is distance v, then we make distance v as this plus this. So after picking u equal to 0, we go through all adjacent of u and relax them using this relax operation. So distances of 1 and 2 are currently infinite. We are going to update them to 50 and 100 because we are getting 0 plus 50 through this and 0 plus 100 through this. So this is what happens in the first iteration. Now we begin our next iteration and we again pick the minimum distance vertex. This time we get the vertex number 1 because its value is 50 and it's not finalized. And we pick only non-finalized vertices. So 1 is picked next time, and after picking 1 we finalize it and we go through its adjacent and we relax them. So when you relax 2, the current value of 2 is 100, you are going to update it to 50 plus 30, 80. And when you relax 3, its current value is infinite, and what are you getting through 1? You are getting 50 plus 200, 250. So both of the adjacent are updated, both of the not finalized adjacent, right? 0 is also an adjacent but it's not updated. So after doing this, our next iteration is over. We again pick the minimum distance non-finalized vertex. This time we are going to get this vertex number 2. Right? There are 2 people contesting for it. So we pick vertex number 2. We go through its adjacent, right? And we relax them. So when you relax this vertex, the previous value was 250. Now you are going to get 100, right? 50 plus 30, 80 is its current distance. And what do you have as an edge? 20. So 80 plus 20 is 100. So we relax this 3 and we get the value as 100. And this is where we stop. We are running the loop only v minus 1 times, not v times. Because once you have finalized v minus 1 vertices, the distance of last vertex must have been finalized. Because after finalizing every vertex, we relax its adjacent, right? So we don't need to run this loop again for this vertex, right? There's no need of it. Although if you run, it won't impact the output, but there's just extra work. So we get our final distance array as this array, and this is our output of Dijkstra's algorithm. Let us now talk about time complexity of this implementation. We have an outer loop that runs theta v times, and inside this outer loop we have 2 loops, consecutive loops, and these loops both run theta v times. So we are together doing theta v work, and this is done in a theta v loop. So overall time complexity is theta v square. We can optimize the time complexity of Dijkstra's implementation. We have done this way to just keep it super simple. See, the one thing that you can do is you can use adjacency list representation. If you use adjacency list representation, then traversing through all adjacent would not be like going through every row of a matrix. It will be like only traversing those adjacent. So if you have k adjacent of a vertex, then you will be taking theta k time, not theta v time, where v is the total number of vertices. So adjacency list representation is going to reduce the number of iterations here. And the other thing that we do here is we use min-heap data structure. With min-heap data structure, we can pick the minimum vertex from min-heap in log v time. So the minimum finding operation can be reduced to log v. So this operation is theta v, and when you use min-heap, it becomes big O of log v. So we have reduced this to big O of log v. We have reduced this loop to only adjacent. And one more thing, in min-heap, reducing a key inside the heap is called decrease key operation, and decrease key operation is going to take big O of log v time again. So this min operation is going to take big O of log v with min-heap. Now, what do we get as an overall time complexity if you use min-heap? So with min-heap and adjacency list implementation, you are going to have this time complexity reduced to big O of log v, right? And this part of the code evaluation is slightly tricky, and we have already done this evaluation in BFS and DFS. So if you are traversing through every vertex and then you are going through adjacency list of every vertex, that's what you do in BFS and DFS. How much time you take overall? You take big O of v plus e time, right? And that's what we are doing here. We are going through all the vertices, not all, v minus 1 vertices, and we can upper bound it by all, right? So we are going through v minus 1 vertices, and we are then going through adjacency list of every vertex, right? So this loop is going to run big O of V plus E time. But inside this loop, we are not doing constant work like we did in BFS and DFS. In BFS and DFS, we were simply printing the vertices. What are we doing inside it? We are doing decrease key operation, which is a log V operation. So big O of E, V into E into log V is the time complexity that we are expanding here. So overall time complexity will become big O of V plus E into log V, because this is big O of V plus E into log V, and this is going to be upper bounded by big O of V log V. We are also doing this in a loop, right? A loop that runs V minus 1 times, and we are doing a log V work. So this particular operation is going to be big O of V log V, and this operation is going to be big O of V plus E log V. So if we add these two, this term is common, so we can say overall time complexity is this much if we use adjacency list and we use min-heap data structure.